everyone. Welcome to the lecture for CE111 for Friday, September 16th. So we're going to continue talking about acid-base reactions today, and we're going to move on to talking about the carbonate system. Whoa, where am I? Okay, so that is not working for some reason. Oh, okay, there we go. My pen is working. This is section 3B, C. We're talking about the carbonate system. The carbonate system is typically what controls pH, the pH of natural waters. So it's extremely important for environmental engineering applications. And there are two main sources of carbonates in natural environments. The first one is the atmosphere, and the second is the dissolution of calcium carbonate from limestone. So two main sources in natural waters, CO2 from atmosphere and calcium carbonate, which is a solid from limestone. And calcium carbonate is also called calcite. So we're first going to draw all of the chemical reactions that can occur when CO2 from the atmosphere dissolves into water. So up here we have CO2 as a gas, and it can undergo gas exchange as determined by the Henry's law constant with aqueous CO2. Okay, so CO2 gas from the atmosphere can dissolve in water, and some of the CO2 that dissolves in the water undergoes a very fast reaction where the CO2 associates with a water molecule, and then we get the species H2CO3. So that's from the addition of a water molecule. And it's actually very difficult to distinguish these two species from each other, so we just lump them together into this species called H2CO3 star. And we typically just assume that the CO2 that dissolves then becomes part of this pool, the H2CO3 star. So H2CO3, the species here, is carbonic acid, and so this is also basically carbonic acid. Now, what's interesting is that carbonic acid, or this H2CO3 star, is a diprotic acid. So both of the hydrogens can dissociate. So let's draw those reactions. So the first dissociation reaction, that is loss of one proton, results in the species called bicarbonate, HCO3 minus. And so this is an acid-base reaction, and the acid dissociation constant, which we're going to give the subscript 1 because there are two of them because it's a diprotic acid, has a value of 10 to the minus 6.35. And then the bicarbonate can deprotonate again to become carbonate, CO3 2 minus. So we've lost another proton here. And the acid dissociation constant, which will give a subscript of 2, for this reaction has a value of 10 to the minus 10.35. 3. Now these dissociation constants also do have a temperature dependency, so this is for standard conditions at 25 degrees, but we're going to assume that for most environmental engineering applications it's not necessary to adjust for that. So if we are interested in what the total carbonate species are, we have to account for all of these different forms. So we're going to give this the symbol C sub T, or in your textbook it's called C sub carbonate. Okay, that's the total mass concentration of carbonate species in any particular water. And I'm going to use C sub T just because it's easier to write. And so that is the sum of these three species, the carbonic acid, H230C star, plus the bicarbonate, plus the carbonate. Now, we are often interested in knowing which of these species is dominant in a particular system, and so we can define some parameters which we call alpha, and alpha is just the mass fraction of each species. So alpha, the value of alpha for H2CO3 star is just the concentration of that species divided by the total carbonate concentration. Likewise, alpha HCO3 minus is just the mass fraction of HCO3 minus over CT, and alpha for carbonate is just the concentration of carbonate over CT. And you can actually calculate the concentration of any of these species directly from, as a function of pH. If you solve, you can rewrite each of these equations in terms of their dissociation constants and the H plus concentration. Okay, and that is done in your textbook, and it's just a bunch of algebra, so we're not going to do that in lecture. But it's a very helpful thing to be able to do. Now it's also really neat to be able to graph the carbonate system, kind of like we did last time for water and for that example problem we did with hydrogen cyanide. So let's now do a graphical representation. Of the carbonate species as a function of pH. So we're going to have on the y-axis the log alpha value, the alpha values that we just defined. We're going to have pH on the x-axis. So let's do some calculations down here. So if we look at what the concentrations are of bicarbonate and carbonic acid as a function of pH, let's look at that. So we want to use the dissociation, or the acid equilibrium constant for those two species. So we have HCO3 minus and H plus divided by H2CO3 star. Okay, so let's rearrange that. so that you can see that the ratio of HCO3 star to H2CO3, sorry, the ratio of bicarbonate to carbonic acid is just equal to the ratio of K1 to the concentration of H+. Okay, that's just rearranging that equation. So if we just plug in values here for K1 and H+, then that will tell us what the ratio of these two species is. So then we can easily see that if the pH is equal to the pKa, then K1 over H+ is equal to 1. And so then we can see that these two species are equal to each other. Oh, I didn't mean that underline. So let's find a point. Let's try to graph that point up here. Let's put it about here. Okay, so we've got 1 point. Those species are equally to each other. So let me go ahead and draw what the graph looks like now. So actually, no, let me show you, go through some of the more calculations first. Okay, so then let's look at the condition. If the pH is equal to 7.35, then K1 over H plus is equal to, so just the value of K1 up there, 10 to the minus 6.35, and 10 to the minus 7.35 down here, then we get a value of 10. So then the ratio of bicarbonate to carbonic acid is a value of 10. Okay, so HCO3 minus is 10 times greater than H2CO3. So that's what happens at about here. Actually, I'm going to put it about here. So here's the pH of 6.35, and at any pH below that, the dominant species in the system is H2CO3, and any pH above that, the dominant species out of this pair is HCO3 minus. So let's just continue this logic again. If the pH is 8.35, then this ratio is 10 to the minus 6.35 over 10 to the minus 8.35, and it has a value of 100. So then we're like out here somewhere. Okay, so very quickly as you go above the pH of the pKa, the basic species starts to dominate. Okay, now I'm not drawing everything on this graph to scale, so don't go interpreting my slopes exactly quantitatively. But then the same relationships apply as we get to the pKa value of the second deprotonation reaction. Then at that pH, the bicarbonate and carbonate species are equal, and above that pH, the carbonate dominates, and below that pH, the bicarbonate dominates. So this graph here is a really nice way of summarizing how the speciation between the different carbonate species changes as a function of pH. And a similar graph is given in your textbook. It's figure 3C2, but the y-axis is not on a log scale. So it looks a little different. I kind of prefer the log scale because it's easier to draw straight lines, and then it's easier to see these tenfold changes in the relative concentration. So I want to give you a rule of thumb back to, we talked about this last lecture. At what point can you assume that one species is so much greater than the other species that you can ignore it in your mass balance or electroneutrality equation? So we can apply what we just did to a rule of thumb. If the pH is equal to the pKa minus 2, so if, let's say, pKa is less than or equal to the pKa minus 2, then you can assume that the acid species is going to dominate. And then in the other direction, if the pH is greater than or equal to pKa plus 2, then you can assume that the basic species dominates. So let's go back and look at one thing. I mentioned that there are two main sources of carbonate species in natural waters. The first is from the atmosphere. So so any carbon that gets added to the atmosphere is going to have to come to equilibrium with water given enough time. So interestingly, as the CO2 concentration has been going up in the atmosphere, about 1/4 of it gets or dissolves into our Earth's oceans. So about 1/4 of atmospheric CO2 is absorbed by the oceans because of this phase partitioning. And that is a good thing in the sense that it's actually keeping the concentrations of CO2 that we've added due to the burning of fossil fuels lower. So the CO2 concentration would actually be higher in the atmosphere if that phenomenon didn't occur. But it also has implications for the ocean. So as CO2 dissolves into the ocean, it is acidifying the ocean. So H2CO3, as you could see from those equations, is an acid. So as more dissolves in the oceans, it's causing a phenomenon called acidification. And you're going to get to do a homework problem trying to calculate what that trying to calculate the approximate order of magnitude of that acidification. Now, why does that matter? It matters because there are a lot of organisms that live in the ocean that make their shells from calcium carbonate. So that includes species like clams, corals, many types of algae, and zooplankton. And these are also organisms at the base of the food chain, so they provide food for fish. They use calcium carbonate as part of the structural parts of their bodies. And so if as oceans acidify, then the carbonate concentration is going down and their shells can start to dissolve. So this is a major risk. Okay, the other topic I wanted to talk about is limestone as a source of carbonate. Yeah, that's my phone ringing. You can just ignore that. So, as we said, one of the components of limestone is CaCO3, or calcite. And interestingly, where that calcite comes from is from sedimentary rock. So sedimentary rock was formed from the deposition of marine organisms whose uh, whose bodies contained calcium carbonate. Okay, so these two phenomena are actually related. When surface and groundwaters come into contact with limestone, then some of that solid calcite is going to start to dissolve. So we can represent that reaction as a chemical reaction, a solubility reaction. So the calcium carbonate dissolves, giving rise to calcium and carbonate. And the solubility product for that dissolution reaction has a value of 5 times 10 to the minus 9 molar squared. So how is this going to impact the distribution of carbonate species? What's going to happen to this carbonate when it dissolves? So if we just write the reaction that it participates in, okay, now we've just added, from that dissolution reaction, we're adding carbonate and to the system, to the whole system, and so that's going to push this reaction back in the reverse direction, and that carbonate is going to, some of that carbonate is going to take up a proton and form bicarbonate. That means that CO3 2 minus is a base. So as a result of this, the pH of, oops, that's supposed to be a therefore, the pH of groundwater that's in contact with limestone is usually greater than 7. Okay, so back to our two main sources of carbonates in natural waters. We have the atmosphere, and so you can actually calculate the pH of pure rainwater. So a drop of rain that's in equilibrium with the atmosphere has a pH of about 5.64. Okay, so it's acidic because CO2, or H2CO3, when it dissolves, oh, I just noticed an error up there, H2CO3, is an acid, and so pure rainwater has a pH of 5.64, so it's acidic. And you may have heard of something called acid rain. That's when you get pHs even lower than 5.64 due to the absorption of other acids into the rain, and we'll talk about that later in the semester. Sorry, due to acids other than CO2. The pH of pure groundwater that's in equilibrium with calcium carbonate, that has a value of 9.96. So it's these two main factors that determine the pH of natural water. And the calculations for each of these examples are given in your book in examples 3C4 and 3C5. Okay, now we need to move on to an additional important feature of having these carbonate species present, and that is that they provide a buffering capacity. So now we need to talk about buffering, and there's a specific term that's used when referring to the buffering done by the carbonate species, and that's called alkalinity. Oops, I spelled that wrong. Alkalinity. So I'm going to try to describe this just conceptually with an example first. Imagine that we have 1 liter of water at pH 7. And we're going to compare that to another liter of water. So this is our first water, and we have the second liter of water. It has a liter of water in it, pure water, and then it has 10 to the minus 1 moles of carbonate species. Okay, or CT is equal to 10 to the minus 1. They're both at pH 7. And the question is, what happens if we add some strong acid to these two different solutions? Specifically, we're going to add 10 to the minus 3 moles of HCl. Okay, we've done this before. So you know what happens in solution 1. The pH is going to decrease so that at equilibrium, which happens very quickly for acid-base reactions, that solution is going to end up with a pH of 3. But what's going to happen in container 2? In container 2, most of the acid that we add, okay, so the HCl is going to dissociate and produce H plus and Cl minus. Well, some of that H plus is then going to combine with the HCO3 minus. And produce H2CO3 star, because these two species have to remain in equilibrium with each other. And there's actually a lot of, so at pH 7, let's go back to our graph. At pH 7, what's the dominant species of carbonates? It's HCO3 minus. You know, there's a distribution between HCO3 minus and H2CO3 star, but those equations have to, or those two species have to stay in equilibrium with each other. This equilibrium constant here that describes their partitioning has to be satisfied. And so if we add 10 to the minus 3 moles of H plus to this system, most of it is going to combine with the HCO3 minus to produce H2CO3 star. So most of the H plus will be taken up by HCO3 minus. And so the pH stays about neutral. In order to decrease the pH significantly, we would have to add about 10 to the minus 1 moles of carbonate, of HCl. So we would have to overcome the buffering capacity that the carbonate species are providing. So there's a huge difference in the response of these two different waters to the addition of this strong acid. And that is extremely important in natural waters. So the carbonate species buffer natural waters. And that is really important because otherwise they would be subject to constantly fluctuating pH, and that's a really difficult environment to live in. So aquatic species really depend on this buffering capacity. So I told you there was a special term given to this buffering provided by the carbonate species. It's actually more general than the carbonate species, but we define alkalinity as the capacity of water to neutralize acids. And in most natural waters, the species that are present that have that buffering capacity are dominated by the carbonate species. So OH- can also contribute, but it's usually present at concentrations that are much lower than the carbonate species. Now this is tricky. When we account for the buffering capacity provided by carbonate, we have to multiply the mass concentration by a factor of 2 because CO3 2- can take up 2 protons, so it has double the buffering capacity as bicarbonate. And we're going to subtract the concentration of protons because they take away from the buffering capacity. So this concept, this definition of alkalinity, was actually given in the textbook back in chapter 2, but I didn't have enough time to bring it up then, and I knew we were going to talk about it again, so I'm telling you about it now. So these are all the species that can accept protons from water. Sorry, can accept protons from any acids that are added to water. So there's another section in the book I want to draw your attention to, which is Exhibit 3C1, and it also walks you through an example of the effect of alkalinity and the definition of alkalinity in a little bit more depth. I want to ask you an important question that relates to this interaction between alkalinity and CO2. So if you add CO2 to water, okay, CO2 gas, so for example from the atmosphere, what happens to the alkalinity? Does it change? So let's think about that. We've got CO2 gas, and in water it's going to become H2CO3. So one way to think about this equation is what we've done is we've added H2CO3 star. Is H2CO3 star in our alkalinity equation? Nope. So just from that alone, you could determine the answer to this question. If we add CO2 to water, does the alkalinity change? No, it doesn't. We just talked a few minutes ago about how we've added an acid to the water, so it affects the pH, but it doesn't affect the buffering capacity. The alkalinity actually stays the same, and that's because we're adding, when H2CO3 dissociates in the water, we're adding a proton and we're adding a base. And these two species cancel each other out. Okay, we haven't added any net alkalinity. So to take this all the way back to where we started, both CO2 from the atmosphere and calcium carbonate present in limestone, they're both important sources of carbonate species. In natural waters. But only calcium carbonate adds to the alkalinity. So only the dissolution. Let's say affects. So a water that had a higher alkalinity has a higher buffering capacity and would be able to resist a pH change better able to resist a pH change due to the dissolution of carbon dioxide. And that's how those two are connected. Okay, so that's it for the lecture. And it's a little shorter than the full time, but that's okay. They'll give you more time to get going on your homework and also review these sections of the textbook that I've referred you to, which will further increase your understanding. All right, I hope you have a good weekend, and I'll see you on Monday.